Hello, everyone, and thank you for being here. My name is Tony Corcelli. I'm an aerospace engineer, a research system administrator, and a student always. Today, I'd like to share an interdisciplinary perspective on a very old concept in physics. We're going to look at how modern engineering fluid mechanics, specifically the concept of a superfluid vacuum, can actually resurrect and resolve a historical pushing gravity model that was discarded centuries ago. To understand this, we have to go back to 1784 and look at Jorge Luis Lesage's theory of pushing gravity. The fundamental question was, what if gravity isn't a pull from within a mass, but a push from the outside? Lesage proposed that the universe is filled with a constant flux of tiny, fast moving particles. When two masses are near each other, they partially block or shield each other from this flux. The resulting shadow creates an imbalance in pressure, pushing the masses together. The beauty of this kinetic model is that it perfectly and intuitively derives Newton's inverse square law. Despite its geometric elegance, the physics community, including giants like Maxwell, Kelvin, and even later on Richard Feynman universally rejected it. And they were right to do so based on the 19th century physics. The model relied on a kinetic gas of flying particles, which created two fatal paradoxes. First, the catastrophic heating problem. For the pushing effect to work, the collisions had to be inelastic. The energy absorbed by these constant impacts would incinerate the Earth. Second, the orbital drag problem. A planet moving through this gas would face a headwind, causing it to lose momentum and spiral into the sun. So the kinetic model failed. But what if the problem wasn't the geometry of the shadowing effect, but the medium itself? This brings us to an engineer and paradigm shift. What if we replace the discrete kinetic gas of these flying particles with a modern concept, a continuous zero viscosity elastic superfluid? Let me illustrate that. This graphic visualizes the transition. On the left, we see the failed kinetic model with its discrete corpuses causing friction, heat, and orbital decay. On the right, we map the same shadowing geometry onto a continuous elastic superfluid. Instead of absorbing kinetic impacts, masses simply displace the fluid, creating a pressure gradient. As we move down the chart, you can see how swapping the medium fundamentally changes the thermodynamic and astrodynamic outcomes. So let's look at that a little closer. By applying the properties of a superfluid, the classical objections instantly vanish. Now, there's no way I'm going up against Maxwell, Kelvin, or Richard Feynman, but um, I'm saying this is another way to look at gravity. First, we have no more heating because the medium is continuous. The force is transmitted via a static pressure gradient, not kinetic collisions. The energy isn't dissipated as heat, it's stored cleanly as conservative elastic potential energy. Second, we have no more drag. By definition, a perfect superfluid has zero dynamic viscosity. Planets can orbit freely through this medium without experiencing any friction or headwind, perfectly preserving stable Keplerian orbits that we're used to. So, if you're looking for a modern physics equivalent, this operates exactly like the macroscopic Casimir effect. In quantum physics, two uncharged plates restrict vacuum fluctuations between them. The higher external pressure pushes them together. In our macro equivalent, spherical masses destructively interfere with the vacuum's elastic pressure capacity. The pressure on the outside, the lateral pressure, is simply greater than the medial pressure in between them. And so the net external pressure pushes the bodies together. And this is what or how I'm visualizing gravity. So, to conclude, this framework isn't meant to overthrow general relativity. I think it's fairly safe. GR remains our most accurate geometric description of gravity. However, by applying the rigorous tools of engineering fluid mechanics and continuum mechanics, we gain a profound, tangible visualization of how space time might operate mechanically. And it rehabilitates the beautiful 300-year-old geometric intuition while remaining strictly compliant with modern thermodynamics. Thank you for your time. I'll leave you with a quote of a more modern physicist, James Evans.